Welcome back. In this lecture, we will start a discussion and on molecular models. Particularly, I will be describing commonly or popular models used to express thermodynamic properties. Okay. So, these are molecular pair potential models, okay, and it is usually used in statistical mechanics calculation. This is useful also in the application of virial equational state, and something which we are going to do this exercise in the later part of this lecture. Let me write down the expression, okay, for a simple model which is basically ideal gas potential model. So, as we already said that we are going to define the potential in general by gamma ij. We could have also used something like a uij, okay, but this is used in the text of this particular course, and thus we would stick to this. Now, for the case of a like particle such as pure fluid, we will be considering II. For the case of unlike species, let us say solute and solution, we will be considering Ij. So, for the case of ideal gas potential, we know the ideal gas do not interact, and thus gamma ij should be 0. Okay. The other most common potential model which is used in statistical mechanics is basically Hartz-Fair potential model. Okay. So, in this case what we have is that it is like a billiard ball, elastic collisions will occur, and thus there are two part of the potential depending on the contact of the particle. Okay. So, if the particle let us say of type I and this is of type J, they are separated more than this center to center distance sigma ij. In that case, if they are separated more than that, the potential is 0. If they are less than or at that location, the potential is infinity. Okay. So, in other words, the potential as a function of r will look like a spike at sigma ij. Okay. So, basically it means this is 0 and then it shoots to infinity. Okay. So, in this case sigma ij is basically nothing but the mean value of the diameter. Okay. Sigma is the diameter in this case. So, it is basically average diameter. Now, using this potential model, we can obtain the virial coefficient, okay, which turns out to be 2 by 3 Na, considering the Avogadro number of molecules here in a mole, and this pi sigma ij cube. Okay. For a specific 2 particle, we can evaluate the virial coefficient very easily by considering this potential model. So, let me just describe that. So, what is a virial coefficient? So, virial coefficient for the second one is defined as minus 1 by 2 v integral double integral Mayer function, okay, which is e to the minus beta potential energy of I and j minus 1 dr 1 dr 2. So, this we can replace this as 1 2. Okay. Now, I can rewrite this expression as dr 1 e to the minus beta gamma 1 2 minus 1 dr 1 2, okay, where remember that beta is nothing but 1 by kT, where k is Boltzmann constant. Now, this is basically a vector. So, if you integrate a vector, you will get a volume V. So, what we have is 1 by 2 integral minus beta gamma 1 2 minus 1 dr 1 2, or I can write this as a simply 1 by s2. This is a volume element in differential form. Okay. Remember, this is a vector. So, this is going to be 4 pi r square dr beta gamma 1 2 minus 1 dr. Now, this is in scalar. Now, if we are going to integrate from 0 to infinity using the potential model. So, since the potential model has 2 parts and it depends on the conditions whether r is less than or greater than sigma ij. So, considering is the same particle, that means of size sigma, we can rewrite this expression as 1 by 2 0 to sigma, okay, 4 pi r square dr plus sigma to infinity 4 pi r square this dr. Now, when r is less than sigma, we know is infinity. So, in that case exponential term will be 0. When gamma is infinity, this is 0, that means this will be only minus 1, and in this case when r is greater than sigma, gamma is 0, in that case exponential term is 1, then 1 minus 1 is basically 0 and this will be 0. Okay. So, what we have is 1 by 2 4 pi sigma q by 3, and this is 2 pi sigma q by 3. Okay, so that is what we have written here, but this is only for pair of molecule. So, if you consider Avogadro number of molecules, it will be for molecular systems, it will be simple if multiplied by Na. Okay, that means you are considering the mole of the system. So, this is how we can evaluate virial coefficient for a simple model such as Hart sphere model. Now, let me describe a bit more on other models which are also available. The reason is that we have to consider other models is because the Hart sphere model do not capture the attractive part. Okay. So, it is only the repulsive part here. On the other hand, we know the molecular system does have attraction, as we have already looked into or went through the intermolecular forces which are available in molecular systems, such as dispersion, dipole-dipole interactions and so forth, okay, inductions, electrostatic and so on. All right, so we must have the attractive part in the potential model, and thus there are various different potential models which have been developed, which depends on different parameters. So, let us consider the one which is a very generic potential model, that is a Mi potential. Okay, it is applicable to non-polar molecules. It is a 4 parameters for pure fluid n m epsilon sigma, and this is written in this form. Epsilon is, of course, we know is a well depth of the potential model. Okay, epsilon is well depth, n and m are the other parameters, sigma is of course the size of the particles. So, this can be rewritten in this form: epsilon ij, mij, nij minus m, and this r0, okay, is used r0 ij divided by r nij, and nij minus mij, and this is again term in terms of mij. So, it appears to be very complex, but the reason for designing it because this allows some flexibility in the potential by parameterizing to a specific molecules or fluids properties and obtaining the right values of n and m. Usually n and m are considered not same. Now, usually this can vary depending on the molecular complexity, but let me just first explain what is epsilon ij. So, epsilon ij is basically nothing but we consider to be geometric mean of epsilon I and j, which are corresponding well depth of a particle I or molecule I, and epsilon j is basically well depth of molecule j. Sigma I j is nothing but the average of the diameter. Okay. Similarly, sigma, we can consider this also, or we can also consider in this form. Okay. So, because one of the important thing is that this has a very sound statistical mechanical origin, whereas this is a bit of weak approximation. So, we can consider either this or that. Nij is considered as the geometric mean of Ni and Nj, and Mij is Mi and Mj. If it is a pure fluid, of course, this becomes much simpler, but this is applicable to a mixed system. Now, if you consider this Mi potential as a function of R, particularly in reduced form where R is reduced by the sigma and gamma is reduced by epsilon, what we can notice is that the shapes is more or less same. The well depth, since it is divided by epsilon, is here -1, but the tail here varies depending on what is the value of n here. Okay. However, you look at this repulsive part is more or less not getting affected by this number n. Yeah. Now, there are special cases which are more popular. based on the my potential. So you have Sutherland potential where Ni's are considered to be infinity and Mi is 6. So when you plug in these values here, these values to this equation, what you get is basically this expression that for r less than r0 ij, which is basically the average kind of diameter, which is basically the mean or the specific diameter or the distance between I and j, this is infinity. On the other hand, when r is greater than this value, you have the epsilon ij and r0 ij divided by r to the power 6. Okay. Now, this is a 2-parameter model because you still have epsilon or r. You can replace r by sigma also, it will work in this way, okay, sigma 0 ij or something like that. So, there are two variables which we have to worry about it. Okay. A more commonly potential model which are by far most studied is with Lino-Jones model, and here the Ni's and Mi's are absolutely fixed. So, what we have is Ni is 12, Mi is 6, and this is sometimes also called 12-6 potential. Okay. So, you have 4 multiplied by epsilon ij, again well depth, and sigma by r here. To note that this is a non-dimensional parameter or non-dimensional term, and the potential model is basically the unit of epsilon. Now, you can compare these expressions here. So, gamma by epsilon divided by r is absolutely infinite here up till this, if you divide by sigma, that is here in this case rij, then you can see this is 1, okay, and from here this is the tail which we get. Okay. On the other hand, if you the Lino-Jones molecule, you can, this is a soft repulsion here, this is a hard repulsion. Remember, this is a hard sphere potential model repulsive part. This is a hard repulsion, this is soft repulsion, and this is the well depth here. You can see again it's a minus 1 because it's divided by epsilon, otherwise it is going to be minus epsilon. Now, what we can do is we can actually try now using this motor potential model and try to connect particularly this one, and try to connect this potential model to van der Waals equation of state, virial coefficient. Okay, and let us first try to evaluate virial coefficient for Sutherland kind of potential. So, this is commonly used for gases. Again, we are worried for gases. So, we are going to consider two body interaction model, and here this is plus infinity when r is less than sigma, minus epsilon sigma by r for r is greater than sigma. So, we are going to consider pure fluid at this point. Okay. So, our interest is B2 between two particle. So, let me first find out B here. So, I'm using the small b here because it's per particle. So, I do not have to write Na here. So, per molecule in that sense. So, we are going to write directly this 0 to infinity. So, I am taking out the double integration and e to the power minus beta gamma minus 1 dr 1 2, okay, vector. Okay. And this I can simplify by considering 0 to sigma. In this case, we have already known this is nothing but minus 1, and this is sigma by infinity 4 pi r square dr, this term which is going to be exponential plus beta epsilon sigma by r 6 minus 1. Okay, remember that beta is nothing, beta is 1 by kT. Alright, so now this is fine, but what about this? How do we solve it? So, we are going to consider an approximation that at high temperature I can write, I can use this exponential term expansion and consider that e to the power x minus 1 is nothing but x. This would be the case for high temperature when 1 by beta or beta is very close to 0. Okay. So, in this case I can replace this by beta, x is nothing but here beta epsilon sigma by r by 6. So, this is an approximation. In that case, what we have is minus 1 by 2 minus of 4 pi sigma q by 3 plus 0 to infinity 4 pi r square beta epsilon sigma by r to the 6. Okay. Now, I can further simplify. Sigma 6 r to the minus 4 plus 1 minus 4 plus 1 from sigma to infinity, and I can divide this 2 to get 2 here, 2 here. So, what we have is 2 pi sigma q by 3, and this will become minus 2 pi beta epsilon sigma q by 3. Okay. So, 3 comes from here, and sigma, this will cancel out the 6 with 3 and 3 from here. Okay. So, now I can simplify this expression as simply omega by 2 1 minus epsilon by kt or beta this, okay, where omega is nothing but 4 pi q by 3, which is an exclusion volume. Okay. So, you got an expression of B. Okay. So, remember that exclusion volume is nothing but if you take this and this, so that this is your sigma. Okay. So, this is the amount, okay, or this is the volume, in spherical volume you are excluding, or this is a volume which we call it exclusion volume. So, considering sigma, it is going to be 4 pi sigma q by 3. Okay. So, that is what we have done that. So, B is now omega by 2 1 minus epsilon by kt. Okay. Now, the next question is how do we use this expression in equation of state. So, let me apply this to P by kt is, so instead of volume I am going to use density. So, this is the virial equation of state in terms of density B rho square plus this. Okay. Now, the density takes care about the molar. This would be this is the molar density. We will be writing like this as n by V. Okay. So, you can get back to the same expression earlier or whatever the earlier in terms of V. So, if you take this as 1 by V, you can divide this n here and you can get that expression in terms of RT also. So, I am going to use this virial equation of state in this form. Okay. And now, I plug this expression. So, I can write this as beta P, this is rho plus omega by 2 1 minus beta epsilon rho square. Okay. I rearrange this expression as beta P plus epsilon by 2 rho square is equal to rho 1 plus rho by 2. Okay. So, I am ignoring the high order term. So, this is rearranging this term here. Now, this I can approximate this term, I can approximate as rho by 1 minus rho omega by 2. Okay. So, this if I approximate this, then I am going to get this expression, and this is nothing but n by V divided by n minus n by V omega by 2. Okay. Or in other word, n V minus n omega by 2. Now, this is, if you look at this expression, this here beta P plus epsilon this by 2 rho square, then this expression has some commonality to the van der Waals equation of state. In fact, this is exactly the van der Waals equation of state. So let me show this to you. So if I rewrite this expression, the last one, expression here, instead of rho I can write n by v square, and beta is 1 by kt. Kt I can take it to the other side, and this I can bring it to this side. Okay, what I get? Pressure epsilon omega by 2 n by v square v minus n by 2 is equal to n k b t. Now this is synonymous to writing here as a n square by v square v minus n b is equal to n r t in molar terms, or p plus a n by v square v minus n b is equal to n k t. So naturally in this case, if you look at it, b is nothing but omega by 2 for each particle. We can consider the exclusion volume contribution from each particle, and a is nothing but epsilon omega by 2. Okay. So this is how you can compare from here. All right. So this is what we have done. Using a simple Sutherland potential, we could get a van der Waals equation of state here. Let me further continue this exercise. Now for the case of Lennard-Jones, as you can see that we have a term on the right hand side which is non-dimensionalized. Okay. Now I can rewrite this expression where instead of writing gamma ij_r is equal to 4 epsilon sigma by r 12 minus sigma by r 6, I can write this as, if I take out here, this is a non-dimensional term, and this 4 multiplied by this non-dimensional term, which now I can put r star r as r by sigma ij, I get this expression, and similarly this would be also due to the fact that r star is this. So I can write this form. So this has become completely non-dimensionalized. Now similarly, I can use this expression in the Mayer function, and if you use this expression, the B2 will be calculated in this form, where r is basically non-dimensional form. So r is in the units of, r star is in the units of sigma. Okay. So let us look at what is typically the kind of virial coefficient for Lennard-Jones. Okay. So what we have done here is that second virial coefficient is being plotted. Now this is divided by B0, which is basically the virial coefficient of hard sphere. That is what it is. Okay. So this is why this is non-dimensionalized, and this is how it increases. Okay. It tells you that at a lower interaction this is more negative, and high interaction it approaches towards 1. So it's far from that. Lower interaction it is very close. So negative virial coefficient indicates there is a cluster of molecules which is close by. If it approaches to large values closer to 0 and beyond, then it indicates that they are far apart. So dispersion or the particles accessibility to the space without being clustered would be indicated by the second virial coefficient having more positive value. Now the virial coefficient has traditionally been also used to see whether we can predict the critical temperature of a given fluid, okay, using virial coefficient, and what is the number of the virial coefficients which can include in the equation of state. So if you can see, or this particular aspect is being plotted here for Lennard-Jones. So this is a reduced pressure, okay, this is a reduced density here. So this is nothing but rho sigma cube, okay, and this is nothing but. So if you include only the in equation state virial coefficient 2, then you can see this is something which is, it increases the pressure and then decreases, okay, and this is at reduced temperature kT by epsilon, which is T star is 1.3, is very close to its critical point, okay. As you increase the virial coefficient, we observe that certain point there is an inflection point here, okay, which only occurs when you include B4 and B5, okay, and somewhere when we include B6, you don't see that change in the curvature as seen in B4, B5. So, which means basically the virial coefficients are makes the equation of state very sensitive, particularly near the critical point. Now, to find the critical point, we can solve this equation. Okay, this first derivative and second derivative should be 0 due to this inflection point, where of course we know this equation here. Okay. Now, this has been done by some people, and if you include B3, you can see only B3 till B3 the Lino-Jones value is the critical point, that is your T star, this is your P star, and this is your rho star, is given in this way. Okay. So, there is a fluctuation in the value. The literature value, which is very precise, tells you that T star, Tc star, that is critical point is 1.31, okay, and the pressure, critical pressure is 0.1279, and this is density is 0.3, okay, and we can see that Tc is, this gets overpredicted. When you include only B5, it's underpredicted, but very close to things. So, up till B5 is fine, but when you include B3, it absolutely overpredicts that. Okay. So, there is a lot of sensitivity, and of course, for B2 there is no way you can obtain the critical point. Okay. Now, we can extend this idea or this understanding to other potential models, but I won't go into details of that. Let me just also summarize what are the other potential models before we conclude this lecture. So, is one of the popular earlier days model has been square well potential. For simplicity, it had a this Hartsfield repulsive term, but then there is a constant attractive term. So, there is no gradual changes in the interaction energy as a function of R, as in the case of Lino-Jones potential. Okay. So, this is very straightforward. When they are close by, it is infinite potential, infinite energy, which positive energy. Otherwise, there is a constant energy up till a well depth lambda, or in this case R, and after beyond that it goes to 0. Okay. That is what this is a 3 parameter model, because you have to worry about epsilon, you have to worry about the sigma, and as well as R. This has to be parameterized based on the potential model or based on the fluids. Now, you can also evaluate B2 for that, but we won't do that. We can straight away use the work done earlier by one of my student. So, here is B2 as a function of T star, and you can clearly see that when you increase the interaction energy range, that is your R, there is a changes in the B2 values. Similarly, we also calculated B3 using something a very sophisticated technique, and here also it depends on the interaction range. Okay. As we already discussed earlier, the B2s are negative for such kind of potential, and as well as Lino-Jones at low temperature, and it increases to 0 or it increases to positive value at high temperature. Okay. Now, you can extend the potential models for a bit of more complicated molecular structures. So, one of those is exponential 6 potential, which is a 3 parameter model, okay, epsilon, gamma, and R0 or sigma. Okay, this is how it looks like. It appears to be very close to the Lino-Jones potential, but Lino-Jones is a 2 parameter model, and thus it may not be easy for many molecules to get fitted in just 2 parameter. The others are high, whereas exponential 6 model has a 3 parameter, and hence many molecules such as alkanes are very well fitted with exponential 6 models. On the other hand, if the molecule is non-spherical, then it becomes a problem using this kind of potential model, and Kihara potential turns out to be one of the good models for that. So, it has epsilon, sigma, A, these are the parameters, and thus it has again 3 parameters here. So, this is a potential model for argon. Again, it may look like similar to exponential 6 or Lino-Jones model. Now, these parameters in the pair potentials, how do we evaluate? Okay, typically we try to fit to the second virial coefficient and gas viscosity and solid state structures obtained from the experiment. We already discussed that how to evaluate second virial coefficient considering very dilute the density. Now, the problem is that when you try to fit the potential model using second virial coefficient, it does not provide a consistent picture of molecule, which you can see from simple argon, okay, and For another case is new pentane. For argon, it may look pretty much okay, because you have what you have done is you can see that for argon different potential model has been fitted, and the way it looks like that there's a lot of large variations in the way the potential models are, but Kihara and exponential 6 and LJ seems to be the good ones, okay, which are close by. On the other hand, if you look at neopentane, there is a large variations in that, and all this yield similar potential, similar second virial coefficient. Okay, so it may not yield that if you have a good, if you have a parameters based on second virial coefficient, it will yield all of the properties correctly. Okay, so in other ways, you consider many different parameters to refine this potential model, but this is an art which we are not going to cover in this course. Okay. Now, if the potential models are, if the fluids are polar, then we have to consider not just the dispersion term, which is typically given by Lennard-Jones, but other terms which will have the dipole-dipole interaction. So, when you include this Lj plus this term, where mu is basically dipole moment, and then we consider such a potential model as Stockmar potential. Okay. Now, I will try to explain argon-argon potential, as we have already seen that you can have many different potential models. So, exponential 6 Kihara, Lj and Squirewell, that if you for the case of argon, how much we lose if we have a potential model which is very simple, such as Lennard-Jones, compared to the very complicated potential model as described by Aziz, and we call it a Aziz potential. So, this is the potential which has a term, the exponential term here, plus this is the expansion, this is a term which includes r to the 6, okay, in the reduced term here, and this other higher order terms with a factor f which is given here. Okay. Now, I will not go into details of how it was evaluated. Okay. So, if you use all these parameters which one can get it for Aziz potential, okay, and then compare that to the Lennard-Jones parameter for argon-argon, okay, then it turns out to be that Lj potential is here, the blue one, and Aziz potential is the red one. Okay, very close by, and thus we lose some information, and Aziz is a very accurate potential. Okay, so we lose some information if we use simple models such as Lj, but then it is necessary that we can use such models analytically or numerically, and thus we do not prefer to take very complicated though correct models, and we would rather prefer to a simple analytical model which can be solved easily. Okay. So, I hope that with this lecture you got an idea of this intermolecular potential, how to evaluate virial coefficient for such a model, okay, and the issues with the parameters as well. Okay, so that will be the end of the lecture. I will see you in the next lecture.